This is KJ here, going over Unit 2, Lesson 1. That's right, you made it through Unit 1. Yay! So our first lesson is atomic structure. This unit explores the history and fundamentals of atomic structure. By following the discoveries of scientists past and present, you will learn about the structure of an atom, the different models used to represent an atom, and the properties of protons, neutrons, and electrons. Yep, little typo there if you caught it. So, lesson 1, early theories of the atom. So let's look at the atomic model. It was developed by Democritus, Dalton, Thomson, and Millikan, so 4 different scientists. Thomson had the cathode ray tube, and Millikan used the oil drop experiment. Scientists and philosophers have studied matter for thousands of years. In this lesson, you will investigate some of the early scientific experiments and theory that helped shape our current knowledge of atoms and matter. Our current understanding of the atom is the result of a long human struggle to comprehend the nature of matter. What we know today is the product of many generations of people who ask questions about the stuff the world is made of. Goals for this lesson. Describe the contribution of Democritus and John Dalton to our understanding of the atom. Describe how the experiments of Thomson and Millikan helped determine the nature of the electron. Describe how the experiments of Thomson and Millikan illustrate the nature of science. All right, so you can get the study guide from here. The nature of matter and atoms has been debated and explored for thousands of years. How many times can you cut a piece of paper in half before you just can't cut it in half anymore? Maybe you cut it 8 times or 12. What if you could cut the paper at the microscopic level? How far can you cut the material in half before it stops having the properties of a piece of paper? Do you think you could keep cutting the paper in half an infinite amount of times? Those are the types of questions that philosophers first proposed and argued about more than 2,400 years ago. Our modern knowledge of the structure of the atom is the result of a 2,400-year human quest to understand the most fundamental aspects of how the world around us is made. And so they have the chemistry timeline. And they're saying, here we go, we're kind of in the classical Greek era. The Greeks defeat the Persians at the Battle of Marathon. And that's when Democritus. So the Peloponnesian War starts. You might remember that. Here it's before the Great Wall of China was constructed. So way back when. And when that was going on was also Democritus. So Democritus hypothesized that all matter is made of small particles, which if you think about how long ago that was and think about stuff that they didn't have back then. They didn't have indoor plumbing, they didn't have microscopes, they didn't have electricity. And back then he came up with this idea, so it's pretty impressive. Democritus thought about the idea of the atom but could not prove it by way of experiment. The concept of the atom goes back to more than 2,000 years ago to the Greek philosopher Democritus. Like others of his time, Democritus wondered whether matter was continuous, meaning it could be cut or divided into infinitely small pieces, or whether at some tiny scale matter was made up of particles that could not be cut or divided. Democritus hypothesized the existence of particles he called atomos, which is Greek for indivisible. So that's where we get atoms from. Atomos, indivisible, or not able to divide. But the early Greek philosophers did not have the technology to prove or disprove their theory of atoms. With the coming of the Dark Ages, science was placed on a back burner of Western thought for more than 1,000 years. So I added Democritus to our notes. He hypothesized the existence of particles he called atomos, or indivisible. There was not technology to test his idea. Early scientists continued to expand on the knowledge of chemistry. The French chemist Antoine Lavoisier changed the way the world thought about matter in the 1700s. Okay, look at where we went from. We went from 400 BC to the 1700s. His experiments on the nature of chemical reactions showed that matter is neither gained nor lost in a chemical reaction. His findings indicated that the mass of the reactants in a chemical reaction is always the same as the mass of the products. So in other words, the mass of what you start with is the same as the amount of mass that you end with. Students of the physical sciences know that matter can neither be created nor destroyed. Lavoisier's findings, while seemingly basic to today's understanding of chemistry, were monumental in the advancement of study. Because think about this. If you have a piece of wood and you put it out on your campfire and you burn it, it looks like there is less stuff left over when you look at the ashes compared to how much room the wood took over. But he said, well, no, you have to account for the smoke and the air and the gases. So that was something that was actually really monumental, that you can't have more or less of a product than what you start with. Matter follows certain laws of nature and did not behave in a haphazard manner. The law of conservation of matter allowed future scientists to study matter in a more understandable way. This law was unveiled in the late 1700s. And what's important is the law of conservation of matter or mass. Honestly, I wouldn't even know what that scientist was known for, even though this is one of the most common laws we refer to. So just the law is important. Matter is neither gained nor lost in a chemical reaction, so the mass of the reactants has to equal the mass of all the products. And that's something we'll be coming back to all year. John Dalton determined that the concept of atoms could be used to describe matter. So Dalton's model of the atom has been improved upon, but is still useful. He was in the 1800s. In the 1800s, John Dalton, an English scientist, came up with an atomic theory of matter. Here are 4 points that are the cornerstone of his theory. Number 1, all matter is made up of atoms. Number 2, atoms are very small, indivisible, indestructible particles. Number 3, all atoms of a given element are identical in mass and other properties. Number 4, chemical compounds form when 2 or more kinds of atoms combine. Now again, these aren't totally correct, okay? So we do know that, atoms are in fact made up of protons, electrons, and neutrons. And we know there's something called isotopes, which if I have 2 different atoms of oxygen, one of them might have an extra neutron, which actually makes it heavier and makes it a tiny bit different, even though it's still oxygen. So again, these are not correct laws. These are just what he came up with as his 4 ideas, which started a lot of the investigations to figure out what the laws really are. Dalton suggested that chemical reactions happen when atoms combine, separate, or rearrange, but the atoms themselves do not change identity in the process, and that's true. We can rearrange carbon to make it the carbon in a tree, or we can have a chemical reaction and it becomes carbon dioxide or carbon monoxide, like in the smoke. What is a chemical reaction? Chemical reactions occur when atoms combine, separate, or rearrange, but the identities of the atoms themselves do not change in the process. And so that is important. Let's go ahead and just add that to our notes. So the notes in this lesson are going to be some vocabulary terms and then, of course, some of the scientists that you need to know as well. And so the next scientist that we're going to add to our list is Dalton. All right, so I just added Dalton's atomic theory and I added the 4 points. And after points 2 and 3, I said we know it's not quite true. So it was a great starting point, but we know more specifications right now. But 1 and 4 are still good. Dalton described the relationship between elements and their atoms. In Dalton's time, people knew that an element, such as a handful of pure iron, was a substance that could not be decomposed into more than one substance by chemical or physical means. So in other words, if you have a handful of pure iron, no matter what you do to it, it's still pure iron as far as what you do to it physical changes. So yeah, we can do a chemical change to it and have it rust, but if you're just talking about physical changes, you can heat it up, you can cool it down, you can bend it, you can break it, it is still iron. Dalton explained this observation by hypothesizing that all iron atoms are identical, just as all sulfur atoms are identical, or all carbon atoms are identical. Dalton stated that since all atoms of a particular element are identical, no amount of dividing a sample of an element would change the nature of that element. So can't magically change iron into gold. Dalton stated that an atom of one kind may combine with atoms of another kind to form a compound, like when it rusts, but iron atoms can never react to become copper atoms. So even if I do a chemical reaction, if I just have iron, I can't make it into gold or something else. In the late 1800s, J.J. Thomson suggested that atoms were composed of smaller particles. Dalton suggested that an atom was a single tiny particle, but other scientists discovered that an atom was much more complex. So in other words, Dalton thought atoms were just solid spheres, like this. So a solid sphere of iron, a solid sphere of gold or copper. But other scientists said, no, there's tinier parts inside. J.J. Thomson used a cathode ray tube to further investigate the composition of an atom. He placed two charged particles on either side of the tube, one with a positive charge and one with a negative charge. Thomson discovered that magnetic and electric fields bent the ray in predictable and measurable ways. This led to his groundbreaking conclusion that the cathode ray is composed of negative particles, which we now call electrons. Thomson thus proved that negatively charged particles were parts of the atom. So what he did was he said, nope, it's not a sphere where the whole sphere is exactly the same. Nope. In fact, there's negative parts inside, which we call electrons. And so let's check this out. In the 1800s, cathode rays were a source of amusement and entertainment, but their nature was not understood. They could be created in a tight beam expelled from a source and attracted to certain magnetic and electrical plates. They could also be deflected by electrical plates. The apparatus that you see was common when J.J. Thomson studied the cathode ray tube. The anodes, kilometers narrow the cathode ray. Okay, anodes, negative. That's how I remember anode. Cathode is positive. Personally, I like cats, so I think of them being positive. A better way to remember the difference between positive and negative, negative. So we have our negatives and our positives. The rays themselves were guided through a magnetic field. Okay, so they used magnets, and the magnets controlled the beam. Thomson noticed that by changing the magnetic fields, the beam was affected. He reached several conclusions, including that the beam was different from other known beams of light, and that there must be particles in the beam. Okay, so he said it's not like light. I can bend it. You know, if you have a flashlight, you can't bend the light by putting magnets next to it. But he said, look at what I'm shooting out here. I'm shooting out these atoms, and I'm able to change the direction of the ray. That tells me something's going on. That's how he figured out parts were negative. Thomson also concluded that the particles must have been electrically charged to behave as they did because of the positive and negative end of the magnets. So you can see here, this is what normally happened, but then it bent. And it bent because of positive and negative. Remember, if you have two positives, are they attracted or do they repel? Two positives will repel. What about two negatives? Two negatives will also repel. So what will attract? A positive and a negative. Here you can see that the greater the strength of one of the magnets, the more the cathode ray is bent. Thomson ultimately proposed that the electrically charged particles were smaller than atoms, and he called them corpuscles. The cathode ray tube itself, with some minor advancements and the addition of an antenna, later became the basis for the modern television. Yeah, pretty cool, huh? All right, so let's add him to our notes. And so I added J.J. Thomson to our notes. He used the cathode ray to discover electrons because the beam bent due to positive and negative charges. And electrons, what are their charges? Electrons are negative. That is definitely crazy important to remember. Thomson asked himself a key question about the nature of the particles in the ray. Thomson then determined the charge to mass ratio of an electron to be negative 1.76 times 10 to the negative 11th coulombs per kilogram. So this is how small that number is, and it's coulombs per kilogram, so every 2 pounds worth. Only has this little bit here. The quantity negative 1.76 times 10 to the 11th coulombs per kilogram is not that important at this point, but a question related to it is, would that quantity vary if Thomson changed the gas in the tube? Because if the charge were always the same, no matter what gas he used, then this would suggest that the particles that made up the ray were common to all types of atoms. Okay, so let's say he used oxygen gas, and he got this amount. Now let's say he went ahead and tried it with neon gas, like neon signs. If he got the same amount, that told him that all atoms have this same particle. If he got a different amount, like